Hello dear learners. In this video, we'll be looking at an application of double integrals. The application that we are discussing here is how the double integral can be used to find the area of a closed region. The formula that we'll be using here is that the area of a closed bounded plane region can be written in the form of a double integral. We are integrating over 1 with respect to y and x. For y, we are using variable limits, that is, it will be a function of x, and for x, we'll be using the constant limits. So let's see a question now. Find the area bounded by the parabola, which is y equal to x square, and the line y is equal to x plus 2. These are the two equations given to us. We'll start by finding the point of intersection of the parabola and the line. For this, I am equating both the values of y in terms of x, that is x square is equal to x plus 2. Shifting the values on the left hand side and making the factors, we'll get the values of x as -1 and 2. So I can substitute these values one by one in any of the two equations. Say if I substitute the value of x in the given line, which is y is equal to x plus 2. So when x is -1, y is coming out to be 1. And when x is equal to 2, y is coming out to be 2 plus 2, that is 4. So the 2 points of intersection here are -1, 1 and 2, 4. So let us now plot these on a graph. So as we already know that the parabola is y equal to x square or x square equal to y. So this is an upward parabola that is drawn here. And for the lines, we can draw a certain set of points. So the 2 points that we have already written before as point of intersection, these are -1 and 1 and 2, 4. So the common area between the line and the parabola, the region bounded by these, is given by these lines. This is the common area. Now I want to write the area of this region in the form of a double integral. So what we can do is, if I have to write the variable limits of y, that is y in terms of x, what I need to do is, I'll draw a line parallel to y-axis. And I'll see from where it is entering the region. This line, yellow line, it is entering the required region from the side of the parabola and exiting it from the line part. So these are what will constitute the variable limits for y, that is y equal to x square, this is the lower limit, and y is equal to x plus 2, this is the upper limit. The variation for x we already know is -1 till 2. So the region of integration is now given by x comma y, where variation for y is from the parabola till the line and for x is from -1 to 2. And we can write it in the form of an integral. We are integrating 1. So integral of 1 with respect to y is y itself. Writing the lower and the upper limit here, I am left with x plus 2 minus x square. Now we are integrating this with respect to x. So the integral will be x square upon 2. The integral of 2 will be 2x and that of x square will be x cubed by 3. And we have written the limits for x now from -1 to 2. We'll substitute the upper limit, that is 2. And for the lower limit, we have replaced x by -1. Solving these two brackets, I'm getting 10 by 3 and -7 by 6. So the required area is coming out to be 9 by 2. And so, since this is an area, so I'm writing the units as square units. So let's see an another example. This time we have two parabolas, that is, find the area of the region bounded by the parabolas y square equal to 4ax and x square equal to 4ay, where a is a positive value. Again, as in the previous example, we are solving these two to find the point of intersection. This time I have taken y from the second equation, that is y is x square equal to 4a, and substituted in the first equation. So this is x square upon 4a whole square equal to 4ax. After taking the LCM and shifting all the values on the left hand side, we are left with x raised to power 4 minus 64a cube x equal to 0. Taking x common, I am left with x cube minus 64a cube is equal to 0, which gives the value of x as 0 and 4a. So when x is 0, I can substitute this in either of the two. So when x is 0, y is 0, and when x is equal to 4a, this also gives us y is equal to 4a. So the 2 points of intersection here are 0, 0 and 4a, 4a. So again, let's plot these two parabolas. Y square equal to 4ax is a right-handed parabola and x square equal to 4ay is an upward parabola. And we already know the 2 points of intersection. They are the origin, that is 0, 0 and 4a, 4a. So this is our required region. Again, if I have to write variable limits for y, that is y in terms of x, so I need to draw a line which is parallel to y-axis. And I can see the line, it is entering into the required region from the parabola x square equal to 4ay, and is leaving the required region when y square is equal to 4ax. So we have written the limits accordingly. That is, the area enclosed between the curves is now given in the form that y it varies from x square upon 4a till 2 times under root of ax, and the variation for x is 0 to 4a. So again, we are integrating 1 with respect to y, and the limits are written with respect to y only. After substituting the limits, we are now integrating this with respect to x. So integral of root x will be x raised to power 3 by 2 upon 3 by 2, and that of x square will be x square upon 3. So these are the values after multiplying with the required constants, and the limits are from 0 to 4a. So substituting the x as 4a and 0, I am left with the required area, which is 16 by 3a square units. Now let's see another way of solving this area. That is, if I have to write the limits of x in terms of y. For this, I need to draw a line parallel to x-axis. It will be entering now in the required region from the parabola y square equal to 4ax, and is leaving the required region from the parabola x square equal to 4ay. So in the first case, value of x is coming out to be y square upon 4a, and if I look at the value of x from the upward parabola, it is now under root of 4ay, which is 2 times under root of ay. The limits for y are 0 to 4a only. So our required region now changes into the value of x is from y square over 4a to 2 times under root of ay. For y it is 0 to 4a. So this time I am integrating 1 firstly with respect to x and then with respect to y. So we have x and the required limits are there. After substituting the limits, I have to integrate it with respect to y, which is similar to the previous one that we have solved. So after substituting limits of y, I can see that the area is again coming out to be 16 by 3 a square units. So we can solve the area either way, either by writing the variable limits for x first in terms of y, or by writing the variable limits for y in terms of x and then writing the constant limits for x. Now there is a question for you, that is, which of the following double integral represents the area enclosed between the parabola, which is y square equal to 9x, and the line x minus y plus 2 equal to 0. You have the four options. You can pause the video and write down your answer, and you can resume when you are done. So let's see what is the solution. This is the correct option that I can see, where we have written x in terms of y, that is the variable limits, and y in terms of constant values. In the other options, we can see when I am writing y first, then the limits, variable ones, should be in terms of x in the A as well as in the D part. In the C part, the value for y is incorrect, the constant limits. For this, we need to plot these values again. So, solving the two equations, equating the values, we are getting y as 3 and 6. So the corresponding values for x are 1 and 4. That is, the point of intersection should come out to be as 1 by 1 comma 3 and 4 comma 6. And if I plot this and draw a line parallel to x-axis, I can see it is starting from the red line, which is the parabola, and exiting the required region through the blue line, which is the equation of line x minus y plus 2 equal to 0. So the limits are written in terms of parabola and then in terms of line, and the variation for y is from 3 to 6. So option B is the correct option. Thank you for watching the video. Hope you will be solving the questions and practicing and getting the correct answers soon.